Okay, here we go. Hello.
Is it all right if we turn in the project later today?
Let's talk right after class. Okay. The answer is yes, but there's more to say. Okay, so let's get started. Again, we're on page 38. A couple of announcements before we begin. So taking our look at the calendar, today is February 3rd. We're going to cover class number 4, which is about constructing antiderivatives analytically. I know that some folks in this room have been eagerly awaiting the day where we get to start doing antiderivatives. We've been doing integrals by areas, and we've been doing integrals on the calculator, and today is your lucky day. And in fact, we're going to be doing integrals for the rest of February with antiderivatives. So all month you get to do antiderivatives. All right, so today's the first day. Okay, project number 1 is officially due right now at this moment. If it's in the folder, if it's on, then it is on time. If it is not on in the folder right now, it is late. I will take it late, but there are penalties associated with it. You want to get it turned in as soon as you can, even if it's late. Next class, 2 things are going to happen. Number 1, project 2 will be assigned. I will hand it to you next class. Number 2, quiz number 1 is due. I mentioned the other day that all the quizzes this semester are take-home quizzes. So quiz 1 is due on Friday, which means I need to hand it to you right now. So I will walk around in just a little bit and hand this to you. The rules are clearly laid out in the first paragraph. It's a take-home quiz, so we want to make sure we know what the rules of the game are. I will just read it very briefly to you. You may use a scientific calculator on this quiz. Note the word scientific, not a graphing calculator, nothing fancy, just a scientific calculator. You may use your textbook on the quiz. You may use our class notes packet on the quiz. You may use nothing else on the quiz, including the internet, a graphing calculator, or people. People meaning your classmates, people meaning somebody in the math studio, no people, okay? So book, packets, scientific calculator, your brain, nothing else. I'll hand this out in a little bit. All right, so let's jump into the packet. Again, on the top of 38, here we go. Daily summary. In this class, we discover rules for finding antiderivatives of certain elementary functions. These rules will be ones that we use repeatedly over the next couple of months. At some point in your Calculus 1 past, there was a day where you wrote down the basic derivative rules that you ended up using for months and months and months, yeah? Today is that same exact day, but for antiderivatives. Number 1 says we know that this integral represents an area, integral from 1 to 3 of 8x cubed dx. What area does it represent? Let's draw a very quick sketch. So here we go. We're going to graph y equals 8x cubed. It looks an awful lot like y equals x cubed, which is what I'm going to draw. And that integral represents an area from where to where? 1 to 3. So we'll put a 1 there, we'll put a 3 there, and we'll shade in. Okay, we know that we can find the value of that integral by typing something into the calculator, but we're going to do it without the calculator. And we're going to do it slowly. I know that some of you guys already know what we're supposed to do, but we're going to do this slowly just the first time through. We're going to use the fundamental theorem of calculus, part 1. We've seen it before. It starts off like this: integral from a to b of f prime of x dx equals. Okay, what's the first symbol we're writing here if we're filling in the formula? This is f of b. That's perfect. It's not f prime anymore. When we saw that fundamental theorem last semester, integrating an f prime involved f's, and then subtract f. Again, not f prime, but f of a. Top thing minus bottom thing, always in that order. That's the fundamental theorem. So that means, in our example, integral from 1 to 3 of 8x cubed dx is just going to be f of 3 minus f of 1, where we are treating this 8x cubed like what? Like f prime, right? We need to view 8x cubed as being f prime, and if we can somehow get our hands on the f function, then we'll be able to just plug in 3 and 1 and subtract. So this is what we are after, is finding a formula for f so that f prime is equal to 8x cubed. And this is why antiderivative is the appropriate tool for our integral. So can you find an antiderivative of 8x cubed? Let's try it. So a good name for our antiderivative is going to be f of x. X cubed, what did it come from? What did you take a derivative of? Forget about the 8, don't worry about the constant, but x to what? Yeah, so definitely it came from an x to the 4th of some flavor, right? If this were the final answer, then taking the derivative would make a 4x cubed. I don't want that, I want 8x cubed, so I have to do something to this ahead of time to build it up to that 8 that I want at the end, times 2, right? It would have been a 4x cubed, we wanted it to be double. And then a quick check, take the derivative, 4 comes down, multiplies by the 2, 8x cubed. Okay, so putting it all together, brand new notation for us here in this next line, number 3. The integral from 1 to 3 of 8x cubed dx is equal to, so we write our antiderivative, that 2x to the 4th. You put brackets around it just like I have there, and then you put the numbers 3 and 1, top and bottom, same order. I've kind of gone a little bit, this is a little bit overkill to put x equals. Normally you just put 3 at the top and 1 at the bottom, and that's what we'll be doing. But I'm just highlighting that these are values of x that we are talking about. And this notation right here with the brackets around the function and the numbers here on the top right just means exactly what we want it to mean. It means plug in the top, plug in the bottom, and subtract. So we plug in 3, 2 times 3 to the 4th, plug in 1, 162 minus 2 is 160. Good? So we're going to practice with that notation today.
Curve from 1 to 3 is 160.
That's correct. That red area is 160. 160 units, square units. Exactly. Yeah, which actually is not so outlandish. I mean, maybe 160 felt big given our picture, but our picture did not do justice to how big 8x cubed gets. If you plug 3 into the x cubed, you get 27. 27 times 8, I don't know, 20 something, 200 and change. Right, and so it's pretty big by the time it's out here to 3. So maybe 160 is not such an outlandish number. Yeah. Okay, so we said that the antiderivative of 8x cubed was 2x to the 4th, but we discovered the other day that that's just one possible correct antiderivative. What's another one? Plus anything. So how about let's just pick a specific one. 2x to the 4th plus 1. Great. We could have done that, right? Let's see if it makes a difference. I really hope it doesn't, because the area of that region is just 160, and it shouldn't make any difference how we get there. But let's make sure that it doesn't make any difference. So if we are going to use our nice brand new fancy shiny notation, then what we're supposed to do is write our new antiderivative formula in brackets, 2x to the 4th plus 1. That's an arbitrary choice that we've made for that constant at the end. And then we'll put the 1 and the 3 just out there. Like I said, I normally don't put the x equals. And that means plug in the top, plug in the bottom, and subtract. Okay, so we're just going to write almost the final answer. When I plugged in before, without the plus 1, I got 162. So now with the plus 1, 163. By plugging that top guy in, minus plugging 1 in. I got 2 before. It's 3 now. So what do we get? 160. So does it make any difference that you pick plus 1 or that you ignore that constant at all? It doesn't, because the subtraction is going to cancel whatever constant you put in the first one, right? It's just going to be, it's just going to go away. And so typically we choose to put a plus 0 at the end. We just don't write it at all. Okay, number 5. Since finding antiderivatives is tied to evaluating definite integrals, which is what we just did up there, we use integral notation to denote an antiderivative. This symbol right here, although it looks very similar to symbols that we've written on this page, is a brand new symbol for us. It's not unrelated, but it is completely new. What's the difference between this symbol and the ones up above? Is it doesn't have numbers on the integral sign. So it does not mean area. It is not that symbol. What it means is antiderivative. So the integral of 8x cubed dx is just 2x to the 4th plus c is our generic constant. We do have to put something there because that symbol I've highlighted means write down the most general antiderivative of 8x cubed that you can. Okay? So quite related, but we use that symbol not to represent area, but to just represent a pure Mathematical definition of antiderivative, most general. Okay, the process of finding antiderivatives is called integrating. So in number 6, let us integrate. Integral of 2x plus 3 dx. So just thinking about derivatives, but backwards. Where did 2x come from? X squared. Plus, where did 3 come from? 3x. This symbol involves writing that plus c every single time. Plus c makes it the most general antiderivative we can write, and we're done. Again, that symbol does not mean area. Looks an awful lot like the area symbol, but it means antiderivative. And honestly, the answers are fundamentally different. Look, the integral of 8x cubed dx from 1 to 3 was 160. This other symbol, which looks quite similar, the answer is 2x to the 4th plus c. Look at the final answers. They're nothing alike, right? 2x to the 4th plus c is one answer. 160 is another. Really, really different, even though the symbols are quite similar. Number 7 has some vocabulary associated with integral notation. The entire left-hand side of this equation, which is the equation we just wrote, is called an integral. So the kind of S-looking thing is called an integral sign. The thing you are finding the antiderivative of is called an integrand, which is maybe not so surprising. What's the name of the x in this symbol? Radicand, right? We got the radical symbol, and the radicand is the thing inside. So integral symbol, integrand inside. The integration variable, this came out kind of light, but you guys can see the arrow there, right, on your page. So that right there is the variable, is the integration variable. It's going to be x or t for a bunch of the time for us. The antiderivative, like kind of a specific one, is x squared plus 3x. That's the simplest one. And then you put this plus c, which we'll call the constant of integration. And if you wanted to read this in plain English, the integral of 2x plus 3 dx is x squared plus 3x plus c. Okay, number 8, a little bit of vocabulary. When the integral sign doesn't have any limits of integration on it, like this one, the integral is called an indefinite integral, as opposed to the definite integrals that do have numbers on them. Okay, next part here says the dx is a necessary piece of every integral. Please include it if you have an integral sign. Probably the very next thing that you should write is dx there at the end. And there'll be some stuff in between, but the dx is quite important. It goes hand in hand with that integral sign. Note that it always goes at the far right, that dx does. For indefinite integrals, the plus c is mandatory. Omitting the plus c will cost you points. See what I did there with the bold and the letter c? It's clever. Also starts with a c. Number 9. Some people on the test, you know, like we'll have a test and you got a quiz there, and so we'll hand out them soon. But what you might do at the end of every answer that you know is one of these, just at the very first thing, just put a plus c right at the end, like a little answer line that you're going to fill in your final answer. Just put plus c's all the way through. You don't have to worry about forgetting it. Okay, finding antiderivatives is going to be important for us this semester. How can we find antiderivatives? We are going to reverse our differentiation formulas. So number 10, we're going to figure out some basic antiderivatives. We'll write the first one in symbols as well as in words. And I'll just say that some of you guys have quite a bit of experience doing antiderivatives, but some of you have little to no experience doing antiderivatives, and that's totally okay. I don't assume any experience doing antiderivatives. But for those of you who have limited or no experience with antiderivatives, today and maybe for the next couple of weeks, your brain is going to be hurting. Like you're going to be thinking about things in a completely opposite way from how you spent a few months in Calc 1. You're all really good at derivatives. This is going to be quite a change for your brain. In the beginning of derivatives, they were probably quite difficult for you as you were first learning all the formulas. But at some point, you got to a place where you were comfortable. You'll get there here too, but it's going to take some time. It's going to take some practice. Right now, this is going to be uncomfortable for some of us. Okay, integral of x to the n dx. This is just doing the opposite of the power rule. Power rule says you take the power, you bring it down in the front, and you subtract 1. That's the derivative rule. We got to do the opposite. We have to add 1 from the power. And then, like kind of given that power, when you take a derivative, is going to come down, we need to put something in here that's going to kill that thing before it comes down. So x to the n plus 1 over n plus 1. Don't forget plus c. And so we promised words here. So our basic antiderivative power rule, add 1 to the power and divide by the old power or the new power? The new power. You're not dividing by the original n, you're dividing by the thing after you have added 1. Divide by the new power. Okay, working our way, which way? Let's go across. Integral of 1 over x dx. It's just the natural log of x. Yeah, I mean, like, this is just a special one. You just have to know the derivative of ln is 1 over x, and so going the other direction, we get ln of x. We'll stick a plus c there. Two little things. Number one, for reasons that are not clear at this moment, but we might talk about, we're just going to automatically put absolute values around that x, just in this formula. Integral of 1 over x for us is going to be ln of absolute value of x. Odds are I'm not going to take points off if you omit them, but in your book you're going to see absolute value. So we'll just get in the habit of trying to include it. Other thing, the first two rules actually conflict with each other because this tells you what to do with x to a power. And 1 over x, this guy, is x to what power? -1, right? So it seems like we've got a conflict here, an overlap. Well, let's see what happens. If we do our new rule here in red, add 1 to the power and divide by the new power. Add 1 to the power, it becomes x to the 0, and divide by the new power, 0. Right, so I probably should have said over here, as long as n is not what number? -1, that's the one that you cannot use that rule on. So that's why we have to have a separate rule for that particular power. Plus c, even though. All right. Integral of e to the x. It's going to be your new favorite one. E to the x, right? E to the x doesn't change when you take a derivative. Likewise, it doesn't change when you take an antiderivative. A to the x, not going to be your favorite one, because we don't know this derivative rule as well as the e to the x rule. So I'm just going to put this, and then we'll amend it. Anybody remember what's the derivative? Yeah, times ln of a is what comes in when you take a derivative of a to the x. It gets multiplied by ln of a. But there isn't any ln of a that popped up in this thing. So we're going to divide by ln of a. It's the same idea as dividing by this n plus 1. Like you got a constant that's going to pop up magically when you take that derivative. So you got to do something ahead of time to kill it before it shows up. Okay, this next row, integral of cosine, integral of sine. This is going to be problematic for some of us. We're all going to get the answer either perfect or almost perfect, but I want it to be perfect. I'm going to write the wrong answer for one of these and the right answer for one of these. So that's like a natural starting point. Right, cosine and sine just kind of swap around, but there are negatives associated with some of these. What do you think? Yeah, this one on the right is wrong. Okay. I wasn't planning on including this, but I just thought of it now, so I will throw it out here. Maybe, where? How about right here on the bottom? So I had a student a few years ago who showed me this, she called it a ladder. Negative cosine x. And I don't remember the student's name, unfortunately, but if I did, I would credit her with this thing. But she showed me this ladder, and she said, okay, when you take derivatives, you just go down the ladder, right? Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. And the derivative of negative cosine, you're just wrapping back up to sine. And so the ladder just goes, okay, well, if taking derivatives is this, then taking antiderivatives must be that. And so, for example, the rules that we just wrote, what's the antiderivative of cosine? Sine, that was in the left-hand column. What's the antiderivative of sine? You go up, wrap around the bottom, negative cosine, right? So if that helps, you can write it down. Okay. Let's see, last row here is kind of more abstract stuff. Taking derivatives of sums and differences works as nicely as you would want, right? You can just separate them in your mind, take the derivative separately, and then add or subtract them at the end. Likewise, when taking antiderivatives, you can do that. And in fact, we use this property probably without even being conscious of it. At the top of this page, we had the integral of 2x plus 3, yes? And in our minds, didn't we just completely separate the 2x from the 3 and then just added up the answers at the end? Right, and so that works nicely with addition and subtraction. It does not work with addition, with multiplication or division, so we'll have work to do to fix that. Yes, Trevor? What one? Yeah, good question. So technically the integral of f of x, if you do the antiderivative, will have a plus c in it. The other guy will also have a plus c, but probably we should call it something else, like plus k. But then having a plus c plus the k, it's just a constant, and so we're going to abuse the letter c quite often in this class and just call it plus c, just a single one. Good. Okay, and then here you got a constant times a function. You can take that constant and bring it right out in the front. Do your antiderivative, whatever it is, and then multiply by the constant at the end. And we'll see how to use that one in this next example here. Okay, number 11 says we're going to use our brand new formulas. We're going to do 11 in far more detail than I would ever require of you. But like I said, some of us have little to no experience doing antiderivatives. I just want to see how we can apply these rules in kind of super slow motion here. But like I said, I'm not going to require as much detail from you at any point. Okay, the first property that we're going to use is the addition and subtraction one, this bottom left one. So we are going to write 3 separate integrals. Integral of 2/5 e to the x dx. What's the next symbol before the next integral? Minus, and then the integral of 3/4 x to the e. That guy also gets a dx. Next symbol, plus, and then one final integral, x minus 1 over square root of x, and that guy gets a dx. So far, so good. You can add and subtract very nicely with integrals. Yeah, we're going to just put a single plus c at the very end after we do all 3 of these. Okay, the next property I want to use is the bottom right one. If you have a constant multiplied by a function, you can bring that constant right outside of the integral. So what's coming in front of that first integral? 2/5, and it's going to get multiplied by the integral of e to the x dx. And the reason we're breaking this down in all these steps is so that we get to one of the few things that we can do an integral of. The integral of e to the x dx is the first integral that we've written in this problem that we actually have a rule for, right? We know what that's equal to. And so that's what we're doing is we're just taking away the stuff that we can deal with separately to get to a fundamental integral that we know. Minus what comes out? 3/4 integral x to the e dx plus. Okay, this next guy, there's no constant to pull out, but I do want to rewrite it a bit. This is really x minus 1 over x to the half, right? Just square root of x is same as x to the half. No calculus, that is a pre-calculus thing, and it's going to allow us to get that integral into a form that we can deal with. Okay, let's start doing some antiderivatives here. Equals 2/5 times integral of e to the x dx is e to the x. Technically plus c, but we're going to abuse our plus c and just put 1 at the very end. Minus 3/4 integral of x to the e is this is x to a power. Yeah? This is the very first rule we wrote in that chart. This is x to a number. And so we add 1 to the power and then divide by new power. And so already, even though we've only got, what do we have, like 8 antiderivative rules, you can see how easy it is to get to hit a stumbling block, to try to apply the wrong rule. You really have to know what's the form of the thing in order to figure out the right rule. This is not a to the x, which was another rule. This is definitely not e to the x. This is x to a power. Okay, plus, this guy is not quite integrable yet, but it's close. We're going to take this thing right here. Notice that there is no property up there for division. So I can't just separate it into two integrals with an x minus 1 on the top and an x to the half on the bottom. No such luck. But we can do one more pre-calc thing, and that's to take that x to the half and split it, put it underneath both of these guys. Kind of running out of space here, so I'm going to do this on the side. This becomes x over x to the half minus 1 over x to the half. Yeah? And we've kind of just seen that x to a power is a really nice thing inside of an integral. So we're heading to a place where they all look like x to a power. What do you do with the powers in this first fraction? Subtract them, right? So 1, the invisible 1 minus the half. So this is really x to the half when all is said and done. Minus. How do I get that thing to be just x to a power? The first one? So the first one has a 1 minus a half. So that one's positive a half. This guy, x to the half, is going to come upstairs and become negative a half. There we go. And so that is a much nicer thing for us to have inside of our integral. Okay, and so we're going to copy everything that was over there in black, unchanged, 2/5 e to the x minus 3/4 e to, x to the e plus 1 over e plus 1. Plus, and now we've got two more power rules that will apply here. Basic idea, again, in English, add 1 to the power, divide by the new power. X to the 1.5, let's keep it as an improper fraction. 3/2, x to the 3/2, divided by 3/2. I'm probably never going to write divided by a fraction, and I will automatically change it to multiply by the reciprocal. You're welcome to do that in 2 steps if you wish. So I'm going to make this a plus 2/3 x to the 3/2. Everybody see that? Instead of dividing by the 3/2. And then minus x to the, so this is this guy here now, add 1 to the power, it becomes half. And then we divide by the new power, which is a half, but instead multiply by 2. So I think this becomes minus 2x to the half. That's kind of 2 steps in 1. Plus c, once here at the very end is sufficient. Okay, like I said, not going to require that level of detail at any point from you guys, but splitting it up when you see addition and subtraction and then taking those constant multipliers in front will become something that is intuitive with a lot of practice. Okay, finally, don't want to give the impression that we can do antiderivatives of anything in the world. For example, x sine of x looks pretty simple, but I challenge you to find a function whose derivative is x sine of x. We will have the tools at one point. You might be able to stumble upon it if you have some time on your hands. X e to the minus x squared. It's not up there. There's nothing that looks like that up there. We will be able to do that one pretty soon together, but not just yet. And then finally, e to the minus x squared, which actually looks simpler than the previous one, right? Previous one we'll be able to tackle in a couple of classes. But this simpler looking one, e to the minus x squared, actually does not have any antiderivative. There's no elementary function whose derivative is e to the minus x squared. So like you can't even gauge the complexity by looking at it. Okay, activity starts on the next page. Make sure you practice with all of our brand new notation and raise a flag if I can help.